In this video, we're going to see how dual variables can be interpreted as marginal costs. We start with the linear programming problem in standard form. We know that without loss of generality, we can assume that the rows of A are linearly independent. Then we assume that there exists a non-degenerate optimal basic feasible solution, and we're going to call it X star. Let B be the corresponding basis matrix. Then we can use the matrix B to write down the basic variables as xb equal to B inverse B. Since we are assuming that X star is non-degenerate, we have that xb is strictly positive. Now we're going to slightly perturb the right-hand side vector B. So in our linear programming problem, we replace B with B plus D. The idea here is that every component of D is very small. We have just seen that the basic components of X star are strictly positive. If we now use the same basis for the new problem, we obtain that the vector of the basic components now is B inverse times B plus D. Now, since B inverse B is strictly positive, if the vector D is sufficiently small, we have that also B inverse times B plus D is strictly positive. Intuitively, this is clear. However, I leave as an exercise for you to figure out exactly how large D can be at most in order for this statement to hold. So if D is sufficiently small, then our basis matrix B leads to a basic feasible solution in the perturbed problem as well. Next, we want to show that this basis is also still optimal for the perturbed problem. To prove that, we need to look at the reduced costs associated with the basis. The formula for the reduced cost is always the same, C transpose minus CB transpose B inverse A. Note that this formula is completely independent on the right-hand side of our equality constraints. So these reduced costs are exactly the same before and after the perturbation. Since our original optimal solution X star was optimal and non-degenerate, then in the original problem, the reduced costs are all non-negative. So we've understood that the reduced costs are non-negative also after the perturbation. Hence, our basis B is still optimal for the perturbed problem. Now I want to look at the optimal cost in our perturbed problem. As always, our formula for the optimal cost is CB transpose times B inverse times the right-hand side of our equality constraints. So in the original problem it was only B, and now it's B plus D in the perturbed problem. So I'm going to write in blue here the new part, which is present in the perturbed problem, but is not present in the original problem. If we perform the multiplication, we obtain CB transpose B inverse B plus CB transpose B inverse D. In the second term, we have CB transpose B inverse, which is an optimal solution to the dual problem that we're going to call P. So we obtain that the optimal cost in the perturbed problem is the optimal cost in the original problem plus P transpose D. So the overall change in the optimal cost from the original problem to the perturbed one is exactly P transpose D, which is P1D1 plus P2D2 and so on and so forth until PMDM. Therefore, the optimal solution P for the dual problem can be used to understand how much the optimal cost will change if the right-hand side of the problem is slightly perturbed. In particular, if we set D to be equal to the vector of all ones, then Pi will be exactly the marginal cost per unit increase of the ith requirement Bi. Next, we're gonna see a different interpretation of duality, again for standard form problems. So once again, we have our primal linear programming problem in standard form on the left and the corresponding dual on the right. To make this explanation easier to understand, we're gonna talk in terms of the dyad problem, which we saw back in chapter 1. If you remember, in the dyad problem, we interpreted each column Aj of the matrix A as the nutritional content of the jth available food. On the other hand, each component Bi of the right-hand side vector is the content of the nutrient I in the ideal food that we want to synthesize. We will see that the dual variable Pi can be interpreted as the fair price per unit of the ith nutrient. So essentially Pi represents how much we are willing to pay for 1 unit of the nutrient I. So let's assume that the PIs can be interpreted in this way. Then we can also understand what is the fair price of the jth food. Everything we need to do is to sum the fair price of the nutrients that it contains. So the fair price of the jth food is P transposed Aj. From the objective function of the primal problem, we know that the cost of the jth food is Cj. And from the dual constraints, we obtain that the fair price of the jth food is less than or equal to its actual price. Now let's use complementary slackness. If xj is strictly positive, then we must have P transpose Aj equal to Cj. This means that if the food J is used to synthesize the ideal food, then it is priced fairly, because its fair price is equal to its actual cost. On the other hand, we know that if P transpose Aj is strictly smaller than Cj, then Xj is equal to 0. This means that if the fair price of the food J is strictly smaller than its actual cost, then we're not going to use that food to synthesize our ideal food. Finally, we can look at the price of the ideal food. This is simply C transposed X star, where X star is an optimal solution to the primal. Also in this case, we can calculate its fair price, which is simply the sum of the fair prices of the nutrients that it contains. So it is P transpose B. Now, from our duality theorems, we know that the optimal cost of the primal, C transpose X star, is equal to the optimal cost of the dual, which is P transpose B. In particular, this equality tells us that the cost of the ideal food is equal to its fair price. In other words, the ideal food should be priced fairly. And this concludes our video on the economic interpretation of the dual variables.